So I'm going to be talking about, I'm going to try to make a case for the importance of understanding data distribution skew when you're dealing with large-scale analytics pipelines, large-scale machine learning pipelines. And in particular, I'm going to talk about the importance and role of data stratification in this process. So my talk is titled Scalable Learning and Analytics, the Role of Stratified Data Sharding. I think we've heard enough talks today about why we're here, why this is important. And so there's a data deluge everywhere, all walks of human endeavor. We've heard some very exciting examples from astronomy, from the physical sciences, and of course, we're in the Bay Area, so of course, the social systems also generate a lot of these. And we also heard a couple of talks on health-related problems. So there's a lot of data. And storing this data is relatively cheap. This is a very dated number from around 2011. It's a lot cheaper these days to store this much amount of data. But the point being that we have an immense ability to capture and store data. But the key question is, what do we do with it? I also occasionally teach courses in our business school. And one of the things I learned from teaching in some of these places is that you always have to start with the value proposition, okay? And the value proposition in these kinds of problems is that data does not exist in isolation. You have to be able to tack it on, take knowledge you've gleaned from other external sources or even other data points and work with it in order to deliver a business edge or a scientific insight or a new type of workflow. This is a quote from a Forbes contributor, and basically she says, there's gold in the mountains of data if you can extract them. So we have data, we have to connect data, and inherently we have a lot of data that has structure to it. The minute you start adding more and more structure to data, it becomes harder for these machine learning algorithms, data mining algorithms, to deal with these kinds of things. So up here I've got examples of linguistic patterns. I've got examples from biological high throughput experiments. I've got examples from traditional sort of social networks. We heard a couple of speakers talk about fluid flow simulations. I've worked on some of these problems looking at wing designs, and the scales and sizes of these kinds of data sets are humongous, but again, there's a lot of complex structure inherent to them. And we heard a lot about different types of containers in the midst. These software systems inherently with the kind of flow of data and control that they have, if you start looking at graphs from these kinds of systems in order to understand where the bottlenecks are, or in order to project where the bottlenecks will be when you start scaling out, then you're dealing with even larger, in some senses, graphs. And I also, in a previous life, used to work at Intel Research, and a lot of our modeling, CAD software modeling, involved the kinds of images you see on the bottom left corner. So all this is great. We have a lot of complex data. We have a challenge. But it's only useful if you're able to extract this kind of information, the kind of useful and actionable information, if you can extract it efficiently. And these kinds of problems are projected by a recent IDC report to be in the neighborhood of about a $200 billion industry. Now, in order to address these kinds of challenges, a key element, and that's part of the reason I'm here, part of the reason why many of you are here, is that we have to lever HPC, high performance computing, distributed computing. I've given some examples here, but I'm kind of an old school as far as HPC is concerned. Most of our work still works off of MPI. I was part of the PVM group way back. before MPI, and before that did a lot of sockets programming. But again, the new age, and one thing that these systems have certainly done is that they've brought more people to the table to discuss some of these challenges. So one of the big advantages I view with MPI and Hadoop and these other things is the fact that they've brought more people to the table as far as trying to understand their algorithms and trying to get high-performance solutions out of them. What I'm going to make a case for in this talk, and this is if you take one thing away, and I realize this is Friday afternoon, and you've got a commute ahead of you. I used to work in the Bay Area. And so the one takeaway from this talk is that I'm going to argue that stratified data placement is something you've got to think about when you're looking at these machine learning, data mining, and analytics pipelines. Data placement being important in itself is not news. This is something that we've been looking at for at least 30 years in the HPC community. We've known for many, many years on the importance of locality of reference, both temporal and spatial locality. Placing related items next to each other, if they're going to be processed together, helps us. Now, what I'm going to focus on in this talk is the need or the thought process behind looking at the payload of the data and why that is important for delivering scalable performance for some of these problems that we're going to be talking about. And in particular, ensuring that there is a clear and pressing need to mitigate this data skew problem that a lot of these applications suffer from. Time permitting, I'll also talk about some of our ongoing work related to interactive response times. So the key idea here is that if you don't have to look at all the data, is there an effective way you can figure out what parts of the data you actually have to look at efficiently and then create a model out of that? This can lead to smaller models, which means faster inference times, and also it leads to more efficient offline costs in terms of training the model if you're processing fewer data elements. And we also have some exciting ongoing work looking at the role of energy in this space as well. So time permitting, I'll talk about that. So before I get to the main parts of the talk, I want to give a one-slide tutorial on this key idea developed by a statistician in the 40s. Okay? His book was first published in 1953, but his first few papers on this appeared in 46 and 48. And he proposed this idea, which at the time was completely novel to statisticians at the time, called stratified sampling. Now, he was a survey statistician, and he was interested in understanding how to get the best out of surveys, especially when you had to go into different types of neighborhoods in some of the larger cities as well as some of the rural neighborhoods. Now, what I have here on this slide is a illustration of 12 individuals colored red, green, and blue. And what I'd like to do, and the basic idea behind stratified sampling or proportional stratified sampling, which is what I'm showing here, is to first group these individuals into strata. Okay, so you've got the blue strata, the red strata, and the green strata, and then proportionally allocate from each of the strata into your final sample. Now, what Cochrane showed and proved is that this kind of approach, if you can create these strata, and that's kind of key, that's the magic, if you can create these strata relatively efficiently, that this kind of approach beats simple random sampling, beats systemic sampling, and some of the other sampling methods that were around in those days. What you can do even further is if you can measure and account for the cost of sampling. And again, he was a survey sampler, so he was interested in how difficult is it going to be to survey sample individuals from particular neighborhoods, hard to get to, high crime neighborhoods. And also, if you could measure, in some senses within each strata, the amount of variation within that strata. If you account for that, you can do even slightly better than proportional allocation, something called optimal allocation. Okay? Now, that's sampling, but here, what I'm trying to articulate is you want to look at the entire data set, because what you might be looking for is a needle in a haystack. Okay? So you don't want to delete stuff. Okay? You want to look at the entire data set, but maybe there's a way in which you can use this notion of stratification to partition that data set. Okay? Now, we understand, as HPC folks, we understand the importance of locality of reference. So the idea here is if you have these groups of, say, individuals that you've grouped together or entities that you've grouped together, well, if locality of information is important, locality of semantic information in this case is important, then you can place entire segments together. So that can be effective. And I'll talk about some applications where that actually works out quite well, not just from a performance standpoint, but also from a qualitative standpoint. However, if your goal is to address the load imbalance problem, and to reiterate again, a lot of these analytics pipelines, machine learning algorithms, involve searching for the best model. So it's a search space. Okay? Think of it as a search space. And if you have no idea when you partition data, and even if you partition it into equal buckets, whether each of those buckets is going to lead to roughly the same amount of search space. So inherently, you're dealing with a load imbalance issue, even if you partition the data equally. So you have to be able to mitigate this data skew. And one way to mitigate this data skew is perhaps each partition should contain a proportionally allocated sample. Like the example I described in the previous slide, now you've got the 12 individuals. Each of these 3 partitions roughly reflects the distribution of the original population. And again, you can do variations of this with optimal allocation and other efforts. Important note here is that for different applications, and even for the same application but different use cases, you may want different partitioning mechanisms. And so it's not a one-size-fits-all solution. So what we've been trying to do at Ohio State, and I'm speaking on behalf of some colleagues as well as some current and former students, is we've tried to create this simple layer that sits on top of some of the current generation big data infrastructure systems. So we go from the MPI and partitioned global address-based systems like global arrays all the way to Hadoop and Spark. We're trying to find this simple layer that will support this, and essentially we'd like to be able to support the kinds of data sets that have this complex structure associated with it. Okay, so the kinds of applications I was referring to earlier. So that's what we'd like to get to. And we have some desirable conditions for this system. We'd like it to be simple to use in the sense that, let's say you have an algorithm and you've built it on this particular system. For the sake of argument, let's say it's Spark. Okay? We would like you to use our layer with minimal intervention, okay? Without too much change to the actual, in fact, we don't touch the algorithm at all. All we're going to do is emphasize some control over where the data you're processing is going to be placed. Again, our goal is to make it efficient, flexible, and in some senses adaptive. But we're not quite there with all these desirable conditions yet. And if you're a football fan, you'll understand what the acronym means. Okay, so what is our challenge here? Okay, our challenge here is, so when we started this project out, one of the first questions we had was, can we simply, in order to generate, the key part of this entire thing is coming up with those strata. So what is an effective way of creating strata? One possible way is to adopt an unsupervised technique like clustering. Okay? The problem with this is it's non-trivial for data with complex structure, and it's potentially extremely expensive. Keep in mind, we want this thin layer that is very efficient. We don't want to take away from the computing resources that these individuals are using. We want to make their algorithm faster. We don't want to make it harder by emphasizing something that's quite expensive. The other challenge is that for many of the problems we're looking at, the data elements themselves can be various. The size of the data elements themselves can vary in size. And clustering typically doesn't have good solutions for these kinds of problems. So I could have an entity that corresponds to, say, a vector of size 100, and another entity that corresponds to a vector of size 10,000. And if I have mixtures of these, it's not very easy for me to develop a clustering algorithm or use an off-the-shelf clustering algorithm. So we developed some approaches to deal with this problem, but it emphasized in 4 steps. So step 1, what we tried to look at was an idea called pivotization, where the idea is simply take this data with complex structure and convert it to a set of relevant features, okay? And I'll give you examples of this in a few slides. The second step is take this variable length set, okay, for each entity, and then compute a sketch of it, okay? And a sketch, in this case, would be something that's a fixed size. Now, once we have these fixed size sketches, it's easier to adapt a fast clustering or sorting algorithm. And I'll give you examples of how we do that. And then once we have the strata, then the question boils down to partitioning and placement, and we'll talk about different sort of applications having different requirements here. So I'm going to go into each of these steps in more detail now. So the first step, as I said, is something called pivotization. The idea here is there is a need to simplify data with complex structure, okay? And our key idea in pivotization is to take this data with complex structure. It could be a tree, it could be a graph, it could be a DAG, it could be a tensor. The key idea is to think globally but act locally. And our idea is to construct a set of features or a vector of local features that collectively captures the global information that is of interest for that application. Okay, on the face of it, this seems like a hard problem. And it is indeed something that's specific to the data and the domain, but fortunately we can stand on the shoulders of people who've come up with some of these creative solutions before us. So let me give you an example. Suppose we're dealing with documents. An idea that we can lever is this work, the seminal work by Broder called shingling, okay? Now, documents may sound easy, so if we look at something more complicated, okay? If we look at images, like the kinds we've been talking about, one can actually use some of these deep learning methods to come up with a learned neural network that can extract these embeddings for you, okay? And also in the case of, in the cases that I'm describing here, there are several other methods that have been developed in the computer vision community for these kinds of problems, okay? And again, we're not inventing any of these. These all exist. For graphs, something that I've worked a fair bit with, we came up with some solutions and others have too. So again, there are ways in a very data type specific manner that you can construct these sets that you can then assert in some senses that if the original entities are similar, then the sets are going to be similar. That's sort of the critical part of this. So once we have these kinds of things, and on the left, what I'm showing you here is an example of a linguistic, this is example drawn from the Penn Tree Data Bank. But I've kind of codified it here to simplify things. These are much larger size trees. But what we have here is a conversion of these tree-like data structures into these 3-element pivots, and a set of these 3-element pivots constitute the pivot set representing these trees. Um, so now, once we have this, once we've taken this complex entity and converted it to this set, now our next problem is that these sets could be of different lengths, okay? And if you want to do pairwise comparisons, it's too expensive, especially if you have a large data set. Similarity computation is very expensive. But again, we can lever some interesting ideas from the theoretical computer science literature and lever this notion of locality-sensitive hashing. And the idea here is that two sets or two of these structures, okay, are going to be, if they have high similarity, their corresponding sketch is going to have high similarity. Okay? And again, for each of the different data types, people have developed these kinds of approaches, and for different similarity functions. So I note some examples here. And again, these are works by Andrei Broder, Piotr Indyk, and Moses Charikar, and others. And moreover, several folks after that have shown that you can even work on more complicated spaces where you're dealing with kernels. Okay? So there are kernel-based similarity functions. We've done some work in this space as well. So there is an effective way where you can take the pivot sets that you see for those original trees on the left side. You can apply this strategy of sketching, and you get a fixed size sketch that you can then compare element-wise. And the number of element-wise matches is going to correspond with high probability to how similar the original sets were. And if the sets capture how similar the original entities are, this should capture how similar the original entities are. And again, the key fact here asserts that if the minimum hash function, okay, match, then the similarity corresponds to a particular similarity function. And you can design this for different types of similarity functions. I've just shown you here one of the simplest ones, which is the Jacquard similarity of sets, since we've converted the complex entity into sets. And what I'm describing in the formula below that is simply to say, if you want to lower the variance of this estimate, you can apply this multiple times. Okay? So don't worry about the details here. Once you have that, the next step is you have an ability to compare these elements and group them into strata. And this is where the slide, the tutorial, the short tutorial I talked about comes into play. Okay, so you can group these sketches. Now, one thing to keep in mind that's very, very important here is that although we're grouping these things by their sketches, we still retain the original data set. We're not touching the original data types at all. All we're doing is using these sketches for figuring out which of those elements need to sit together. And that's going to be defined in the next step. But here we have different ways for creating the strata. One could be a simple sort function. Okay? Another could be a sketch cluster algorithm, a really fast, linear one-pass sketch algorithm. Or something slightly more complicated where you take two passes over the data set, but you have better clustering ability. Depending on what your requirements are in terms of quality, you have choices there. Now, once you have all this information, the only thing the application developer has to give you is how do they wish to partition the data, or some insight of what they're trying to optimize. So this is going to be guided by application hints. So this is the only place where the developer has to specify something to the system. And depending on the ways, the flags the application developer uses for this, we can either use proportional allocation if the goal is to mitigate skew, or if it's really important to have semantic locality, we can try to group related items together and place it together. And if you want optimal allocation, which I'm not going to talk about, you could do that as well. Okay? And all-in-one is an example of a mechanism that puts all related items, all related entities together. Now again, to reiterate, the note at the bottom is essentially asserting we just use these sketches to come up with a fast way of computing which elements have to be put together. But again, we're running the application as is without any changes. Okay? So we have to operate on the original data set the original application was written in. So the original data elements are simply going to be packaged together into these containers, or I should use another word given what we heard in the afternoon, into these shards, and they can then be processed by the application. So just to reiterate, we start with our original data elements, our original data sets. We apply these pivot transformations to convert them into a variable length sets which capture the global information of interest while acting locally. We apply a sketching algorithm, okay, and we can apply this for different types of measures of similarity and for different types of entity types or data types. We then use these sketches to cluster or create strata, and that's what I'm showing you here as S-number, S1, S4, S128. And then we can use different methods to partition depending on what the application specifies. In this case, we're using something called, in the example I'm showing you here, we're using something called an all-in-one partition. So the entire strata, S4, appears in partition P2, but also appears in partition P8. So again, this supports replicability, which is increasingly common in some of these big data systems. So that's sort of the flow. Now, another important thing to point out here is this is embarrassingly parallel. You can process each data element almost in its entirety, independent of the other. So every sequence of operations you're seeing here across each of these lines can happen in parallel. So I'm going to give you some highlights on some results we have. What I'm going to report here are end-to-end wall clock times. It is going to, for the cases where we're applying these stratified data placement algorithms, is going to include the time for doing all these steps. We've evaluated this on a host of different applications and algorithms on a host of different systems, but I'm going to just show you a couple of examples. All the applications are run straight out of the box, the only exception being the application hint that is being provided. So I'm going to first talk about a linguistics application. If you work in NLP, you know some of these problems are incredibly compute intensive, and in some cases also processing large amounts of data. I'm not going to go into the details of what the algorithm does, but I'm just going to give you a high-level picture. What you're seeing here, the blue line, y-axis is log scale execution time in seconds. X-axis is number of nodes. Blue line is a standard round robin or random placement algorithm. Doesn't do anything smart. The gray line corresponds to using 2 of the steps in our approach. Not all 4, but 2 of them. And the red line is using all 4. What you're seeing here is about 2 orders of magnitude improvement in terms of execution time. And it's running straight out of the box with no changes. All we're doing is changing the way we place data. So why is this? Recall that I said that at the end of the day, many of these problems are search space problems. You're searching for a model. You're searching for patterns that best summarize a particular problem you're looking for. You have no idea whether if you randomly break these things up, if the search space you're allocating to each processor or each node is exactly the same. So you have to look at the distribution, the data distribution. In fact, when we drill down on some of these results for some smaller scale experiments, we see this problem. What I'm showing you here is for really small data sets. These are for a couple of really small data sets and running on 8 processors. The dark bars are what we get when we apply stratified placement. And again, this is log scale, so there is some variance, but we're pretty good. You can see they're fairly flat. Now, if you don't pay attention to the data distribution, each of the nodes is going on and looking at a very distinct search space, much larger search space than if they had a good distributional objective here. Okay? And this is, they're spending a lot of time on parts of the search space that they could very easily have pruned if they had a more global picture of what was going on. Now, both of these, just to reiterate, produce the exact same set of results. This is not a probabilistic algorithm. It's very deterministic. Both of these are producing exactly the same results. What is different here is that if you do not pay attention to data skew, you're losing about 2 orders of magnitude in speed for these kinds of problems. Here's another example. So part of this is joint work that we did with colleagues at Microsoft Research. But this particular experiment was something we did at Ohio Supercomputer Center. This is an example. So in the previous example, I forgot to mention, one of the things was we were trying to mitigate data skew, so we used proportional allocation. In this problem space, what we'd like to do is take these large graphs and come up with an effective compression scheme. And once you've compressed the graphs, you can then apply standard algorithms like PageRank or whatever algorithms you favor on these graphs, on the compressed graph directly. It's a critical application for search companies. Okay? Many of them use some variations of these kind of graph compression algorithms to store and manage their data. Now, a key requirement for this particular application was that you want semantically related entities next to each other. You want them processed together. Now, why is that? Think about it. How does data compression operate? Okay? It's looking for sequences of common patterns. Okay? So you want semantically related elements to be together so that the net compression effect is good. Okay? And what we show here is that if you don't pay attention to this kind of stratification, you're going to lose out on compression efficacy, on a compression effectiveness. So again, this is a different type of stratification, but you want to pay attention to the data distribution again. And again, I'm not showing you some of the follow-up work, but once we compress the data, you can apply some of these algorithms significantly faster because you're operating on a much smaller data set that can comfortably fit, in many cases, in the L3 cache of modern systems. And we did some comparisons using this method with some of the standard graph partitioning methods. And the results were actually quite compelling, in the sense that when we compared with Metis and some of the others that some of the DOE labs have put out, what we are optimizing for is different, and we're dealing with a different set of problems. We have some topological characteristics here that are quite different. But because we're looking at some of these and accounting for some of these topological characteristics and some of these semantic information, we are both much faster and we're able to compress much better on some of these problems. I'm running out of time, so I'm going to go through this part a little quickly. The last part of my talk here is to show that you can employ this kind of stratification while accounting for heterogeneity that's part of pretty much any modern data center, where you swap out an existing machine with a new machine. It has slightly different configurations, slightly different capabilities. And so when you have this kind of heterogeneity in both compute and storage, you're going to have to rethink how you place data. And moreover, in many of these kinds of problems, these data centers, maybe they're geographically distributed, or maybe they're closer to the grid tie. Different machines within the same data center could have different capabilities in terms of how much clean energy they have access to. And so if you are concerned about clean energy usage, that is something where, again, these kind of things can play a role. Now, I'm not going to go into the details because I don't have time here, but we built a system working collaboratively with OSC and others. The high-level sort of takeaway is that there is essentially a Pareto frontier here. Now, a Pareto frontier basically suggests you're trying to optimize for two or more constraints, typically two, in this case two. Amount of dirty energy consumption and performance, or speed or efficiency. And let's say you have 4 nodes, one of which can operate completely on clean energy and 3 cannot, just as an example. The optimal from a clean energy perspective is to run the entire workload on that one node. But obviously that's not going to give you the most efficient solution in terms of running. So you have to play with both of these parameters depending on where you sit. The other thing is you could have heterogeneity in compute and I/O resources. So accounting for that also plays a role. So what I'm showing here is that up here in the, it might not be clearly visible, there's a yellow dot called stratified on each of these graphs. The y-axis is the amount of dirty energy consumed for some of these problems, and the x-axis is execution time in seconds. And if you don't pay attention to heterogeneity and you use just the basic stratification procedure I laid out, which is much more efficient than a random or a round robin or something that's placement agnostic, you are going to be that dot. However, if you pay attention to these things and model them and place your data accordingly, you can sit anywhere on this Pareto frontier, depending on what you'd like to optimize for. You'd like to optimize for greater performance, faster, then you can sit anywhere on this Pareto frontier. So this was a piece of work that appeared last year at ICPP. All right, I'm at the end of my talk. Key points. Today's analytics world has a lot of complex structure, machine learning pipelines, and data mining algorithms. I've tried to make a case that accounting for data distribution and stratified data placement is important. We're trying to build a layered system, a simple layer that sits on many of these different systems. And we've examples that show that you can get, for some of these applications, up to 2 orders of magnitude improvement over the state of the art for some of these tasks. And we have preliminary evidence that suggests that accounting for this kind of information on modern data centers may be a useful problem to be looking at from the perspective of how much clean energy these systems can use and accounting for the heterogeneity in them as well. With that, I really thank all of you and the organizers. And this is joint work with collaborators at OSU and a couple of students who've since graduated, and of course, the funding agencies that supported a fair bit of this work. Thank you. I'm happy to take questions. Yeah. Which one? Yeah.
So what you're saying is that even without stratification or with stratification?
So what I'm saying here is that all of these points, red and yellow, use stratification. The red points account for heterogeneity of computational resources and I/O, as well as heterogeneity of the fact that some machines may be able to tap into green energy more effectively. If you have a geographically distributed data center.
Is there an optimality beyond stratification?
Yes, yeah, it is. Yeah.
Just the observation that we were talking about pivot, sketch, and stretch. I thought that was ironically parallel to what
Who?
Was there a biologist or a geneticist one of your team who were looking at this development of pivot, sketch?
So there have been these kinds of ideas that have been used in different domains. As I said, I mean, this idea of sketching or this idea of computing these pivot structures is not sort of, not all of it is completely new to our work. So there are examples of this. So for instance, the sketching stuff, broader, I mean, so I think he was at DEC SRC at the time, working on Alta Vista, if you remember that. Yeah, so this was a part of one of the Alta Vista core algorithms. So, but biologists, anyway, to get back to answer your question, yes, geneticists and biologists have looked at these kinds of problems as well. One of the papers I cite there is by Przulj, and she's done a lot of work in graphlets with protein interaction networks.
The big irony is you go back and look at Mendel's pea plants back in the
Uh-huh.
it models that. It doesn't use the same terminology, but it basically does what they've done.
At some level, yeah.